Yes, good morning, students. Is it audible now?
Yes, ma'am.
Okay. Good morning, everyone. Here, today we'll discuss some concepts or some problems related to the expectation. So, in the last class, we have solved problems on CRV, DRV, and MRV. That is nothing but continuous, discrete, as well as the mixed random variables. So, today, here we'll take some examples related to expectation. So here we have discussed the concepts of expectation in the previous classes. So for the discrete random variable, we have seen the equation of the expectation. So in the first moment, that is m1 about the origin, which is considered as the mean. So that is defined as x bar is equal to summation xi p of xi, where I takes the value from 1 to n. So this is the equation for the mean. And along with this, we have also seen the equation for, just a minute. We have also seen the equation for the second moment about the origin, which is considered as M2. So here, the second moment about the origin, so it is usually taken as the mean of the square of a random variable x. So, and it is given as expectation of x square, which is considered as M2, is equal to summation x square into p of x. And other than this, we have also seen the square of expectation of square of the random variable about the mean. So when mean is given, so in such cases we can calculate the value using the equation x minus mu x whole square into p of x. So this whatever the equation that we'll be using, so that gives the value of the variance. And if we take the square root of the variance, so it gives the value of the standard deviation. So these are the equations for the discrete random variable. Similarly, the same equations, it can be expressed in terms of integration for the continuous random variables. So for the continuous random variable, so the mean about the origin, it is given as integral x into f of x dx, and which is taken as m1. And similarly, the second moment about the origin, that is nothing but the square of the random variable, expectation of the square of the random variable, it is given as integral x square into f of x dx. And about the mean, so the expectation, or in terms of variance, we can call that as variance of x is equal to sigma x square integral x minus mu x whole square into f of x into dx. So using which you can you'll be able to calculate the standard deviation. So all these equations we have seen in the previous class. Along with that, we have also seen some properties for the expectation. So here using this, so here first we'll take some examples which are given in the textbook. So later we'll take up the exercise problems. So now let us consider the first example. So to which we are going to apply the expectation. So here the expectation, whatever the first moment, second moment, and the variance equations we have seen. So suppose if it is applied to the uniform random variable with the PDF, fy of y is equal to 1 by y2 minus y1, so which is available for the interval y1 up to y2, and it is 0 for other values. So if suppose if you are given this PDF, so then how you are going to calculate the expectation of the random variable about the origin, and the square of the random variable about the origin, and the square of the random variable about the mean. So here we'll see how to calculate this. So here I'll just go on solving this. Along with me, you can also solve and copy the problem. So I'll just share the screen here. So here we'll start. So here we are given with fy of y is equal to 1 by y2 minus y1, and which is available for y1 less than y less than or equal to y2, and it is 0 for other values of y. So here you can see that y2 is greater than y1. And we are using this PDF. So whenever we are given with the small f, so here it is understood that this is nothing but the PDF. Suppose if it is given in terms of capital F, then it indicates the CDF. So here given this PDF, we are asked to calculate, we can calculate the expectation of the random variable capital Y. So here when you say the expectation, so here it means expectation of Y, capital Y you can write. Capital Y, and along with this we can also calculate the expectation of square of the random variable and expectation of square of the random variable about the mean. So about the mean is represented as mu y. So here whatever the equations you have seen previously, that was in terms of capital X. So whatever the expectation equations we have seen, that was expressed in terms of the random variable X. So the same equations, they can be written in terms of the other random variable which can be expressed in other uppercase letters. So here we have given with the random variable represented by capital Y. So here we'll see how to calculate this expectation of Y. So here first we'll take up the first equation. Okay, expectation of Y. So what was the equation? Expectation of y, it is nothing but the mean. So mean, it is represented as mu y. So which is obtained by using the equation integral minus infinity to plus infinity y into fy of y, which has to be integrated with respect to dy. So since it is given as a uniform random variable, it means that we are solving the problem on the continuous random variable. So for that reason, so here we have written the integral equation. So here according to the given PDF, so as we have seen that this fy of y, it exists only between y1 and y2. So here this integral, it is going to be changed from minus infinity to plus infinity as y1 up to y2 into y. Fy of y is how much? 1 divided by y2 minus y1, which has to be integrated with respect to y. So now in the next step, what you can write? So here 1 by y2 minus y1, that can be taken outside, and integral of y is y square by 2 with the integral range y1 to y2. So now, if you simplify this, if you substitute the lower and the upper limit, so here we get 1 by y2 minus y1 into y2 square by 2 minus y1 square by 2 minus y1 square by 2. So this is equal to 2 is common. S2 is common. You can take it outside. 1 by 2 into y2 square minus y1 square all divided by y2 minus y1. So here what is this y2 square minus y1 square? How it can be expanded further? So this is similar to a square minus b square, right? So here as you know, a square minus b square, it can be expressed as a minus b into a plus b, right? We knew this. So here using that, we can rewrite this equation as 1 by 2 y2 minus y1 into y2 plus y1 all divided by what? y2 minus y1. So here y2 minus y1, y2 minus y1 gets cancelled. So here we get the mean about the origin as, that is, expectation of y, capital Y, is equal to mu y, which is equal to y1 plus y2 divided by 2. So this is the mean for the uniformly random variable with the PDF 1 by y2 minus y1, which is distributed between y1 and y2. And in the next part, you can go through these steps I'll just show it once again. I'll not explain, you just observe what is being done. So this is the PDF given. We are asked to calculate the mean square of the expectation of the square of the random variable about the origin, square of the random variable about the mean. So here first we have taken to calculate the expectation of the random variable y, which is nothing but the mean mu y. And since it is a uniformly distributed random variable, you will go with the continuous random variable equations, not with the discrete summation ಹಾಕಂಗಿಲ್ಲ. So here we'll go with the integral. So here integral equations ಏನಿದೆ ಮೀನಿಗೆ y into fy of y dy. So ಅಲ್ಲಿ x into fx of x into dx ಅಂತ ಬರ್ದಿರ್ತಿದ್ವಿ since we were given the random variable x. So now since we are expressing random variable as y, you just use these steps. Okay, next we'll take the calculation of expectation of square of the random variable. So this is capital Y. So here this is nothing but we are calculating the expectation about the origin. So this is equal to, so what is the equation for this? Or remember one thing, this is not the variance. So this is just the second moment about the origin, second moment of a random variable about the origin, that you need to remember. So this is integral minus infinity to plus infinity. First we'll write the original equation, then you can replace the integral values. So here this is y square into fy of y with respect to dy, we need to integrate. So here what we do now? So here we'll change the limit minus infinity to, just a minute. Is equal to, we'll change the limit minus infinity to plus infinity as y1 to y2 and y square, and fy of y it is replaced as 1 by y2 minus y1 with respect to dy. So once again you are going to take this 1 by y2 minus y1 outside. So here you can take 1 by y2 minus y1 outside the integral. And what is the integration of y square with respect to y? Y cube by 3 with the limits y1 to y2. Right? Now substitute the limit. This is equal to 1 by 3. 3 I will take it outside as it is a constant, into y1 in y2 minus y1 into y2 cube minus y1 cube. So now here you need to apply a cube minus b cube formula. So here what is the equation of a cube minus b cube? It has to be expressed in terms of the factorization. So here what is the equation? So here this can be further written as is equal to 1 by 3 into y2 minus y1, and this a cube minus b cube formula if you apply, so this will be resulting in y2 minus y1, that is nothing but a minus b into y1 square plus y2 square plus y1 y2. You can multiply and you can verify. It will be yielding the result y2 cube minus y1 cube. So here y2 minus y1 gets cancelled. So you need to remember all these formulas, a square minus b square, a cube minus b cube. So all this, if you remember this, it will be able to solve the problem very easily. So here the square of the random variable expectation, it is simply equal to y1 square plus y2 square plus y1 y2 whole divided by 3. So this is the answer for the second parameter, which gives the expectation of the square of the random variable. And thirdly, we are asked to calculate the expectation of square of the random variable about its mean. That is nothing but we have to calculate the standard variance. So write the equation of variance. Hold on. Just take the print screen here. So now expectation of square of the random variable about the mean. So its equation is integral minus infinity to plus infinity. So here we have what is the equation for us? So we had x minus mu x whole square. That is nothing but here we'll be expressing that as y minus mu y whole square. You just go with the equations that is been shown uh, at the beginning into fy of y with respect to y. So now what we do? Substitute the equation of fy of y and change the integral also. So this is equal to integral y1 to y2 y minus mu y whole square into fy of y is 1 by y2 minus y1. My goodness. Into dy. With respect to y, we need to integrate. So now what we do? We'll take 1 by y2 minus y1 outside and then integrate y minus mu y whole square with respect to y. So here before that, I will just expand that using the formula a minus b whole square. A minus b whole square formula is a square plus b square minus 2ab. So you are using that, you can rewrite this equation as y square plus mu y square minus 2y into mu y, which has to be integrated with respect to y. Now you can split this integration into three terms because we have the addition and subtraction. This can be split up. So here integral y square dy plus integral mu y square dy minus integral 2y mu y with respect to y. So limits is same for all, that is it ranges from y1 to y2, that you can copy it later. 1 by y2 minus y1. What is the integration of y square with respect to y? Y cube by 3 plus mu y square is constant and integration of 1. If you don't have anything here, you have to assume that as 1. So here integration of 1 with respect to y is y minus 2 mu y is constant, take it outside, integration of y with respect to y is y square by 2. So for this you will be applying the limit as y1 to y2 as a whole. I am taking, not as individual. And for this, if you substitute the upper and the lower limit, so this will take some time. We can go with my notes also. 1 by y2 minus y1. So here if you substitute the upper limit and the lower limit, and if you go on simplifying this, I'll just show for the first one. So here this will be y2 cube minus y1 cube by 3 plus mu y square. You have to substitute the equation of mu y also. So into y2 minus y1 minus 2 gets cancelled. I'll just remove this into mu y y2 square minus y1 square. So this is obtained after substituting the upper and the lower limit. Next what we can write? 1 by y2 minus y1, and again you have to apply the formula of a square minus b square, sorry, a cube minus b cube. So here as we have seen previously, so this can be done as y2 minus y1 into y1 square plus y2 square plus y1 y2 all divided by what we have 3. And what is mu y? Mu y we have calculated. Mu y is calculated. What is the equation for mu y? You can see here y1 plus y2 divided by 2. That you can substitute. So substituting that, here we can write that as ಎಸ್ mu y ಸ್ಕ್ವೇರ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದ್ರೆ ಎಷ್ಟು ಬರುತ್ತೆ? ಸೊ ದಿಸ್ ಇಸ್ ವಿ ಹ್ಯಾವ್ y1 plus y2 whole square divided by y1 plus y2 divided by 2 we have. So 2 square ಮಾಡಿದ್ರೆ 4 into y2 minus y1 minus mu y is y1 plus y2 divided by 2 we have. So into y2 minus y2 square minus y1 square is there. So that is nothing but a square minus b square formula. So here if you expand this in terms of a square minus b square, so here we can write y2 minus y1 into y1 plus y2. So if you just simplify after substituting the mu y equation and expanding the equations of a cube minus b cube and a square minus b square, so finally we left with the equation. I'll just write the final answer. You just go on simplifying because it will take time. All the steps is written. Only the thing is you need to simplify this. Y1 square plus y2 square minus 2y1 y2 all divided by 12 you will get. So this is nothing but, so here if you observe this, this is nothing but it is in the form of a square plus b square minus 2ab. So here we can write that as y2 minus y1 whole square divided by 12. So this is the equation of variance. So here whatever the expectation of the square of random variable about the mean we have calculated. So this gives the value y2 minus y1 whole square divided by 12. Have you understood this? If you have any doubt in this, you can ask me. Shall I move on to the next problem?
Yes, ma'am.
Any doubt? Is it clear? We'll take up with the next example. Yes, pardon. Shall I go to the next problem?
Yes, ma'am.
Yes, ma'am.
Okay. Now, let us apply the same thing to calculate the mean and the variance for the normalized Gaussian random variable with the PDF whatever we have taken for the Gaussian random variable. So here actually the PDF for the Gaussian random variable is it is given as fz of z. So usually for the Gaussian distribution, we'll take the random variable z. So this is given as 1 by root 2 pi into e to the power minus z square by 2. So this is valid for minus infinity less than z less than infinity. So for this much calculation is not shown directly. I'll just write the answer. So here given this PDF, so we can ask to calculate the mean. So here mean is nothing but the expectation of the random variable z about the origin, that is represented as mu z. As Gaussian distribution, Gaussian random variable is also taken as the continuous. So here again we'll go with the integral equation minus infinity to plus infinity z into fz of z. So this is the equation which has to be integrated with respect to z. So this is equal to integral, already the integral range is same, minus infinity to plus infinity, z, fz of z is 1 by root 2 pi into e to the power minus z square by 2 dz. So for this, you can take 1 by root 2 pi outside, 1 by root 2 pi outside, integral minus infinity to plus infinity z into e to the power minus z square by 2. So for this, the mean, it can be directly calculated. So whatever this integral value you are seeing, so here you can see that we have simply a z, which is nothing but it consists of a odd integrand. That is, it is having a power 1. So whenever you will be given such values, so odd power idre, so this integral value, it will be equal to 0. 0 irutte. So here the mean, it will be equal to 0. So directly you can show this result. For the odd integrand, the integral value minus infinity to plus infinity z e to the power minus z square by 2 into dz. So always it will be equal to 0. And similarly, you can calculate the variance sigma z square, that is nothing but expectation of z square or z minus mu z whole square you will be writing. But here mu z, it is obtained as 0. So here, as already I told that, so here the variance is nothing but you will be calculating the expectation of the square of a random variable about the mean. But here the mean is 0. So here simply it is equal to expectation of z square. So for that reason, so we have not taken the calculation of the second moment about the origin. So here for this Gaussian distribution, both are same. So if this is equal to, what is the equation in terms of integral? Minus infinity to plus infinity z square into fz of z. So that fz of z, it is directly written as e to the power minus z square by 2 dz. So for even integrand, so always remember for even integrand, so here we have root 2 pi also. So this can be further written as 1 by root 2 pi is taken outside, 1 by root 2 pi integral minus infinity to plus infinity z square e to the power minus z square by 2 into dz. So here for, since we have the even integrand, so previously mean calculate ಮಾಡಬೇಕಾದ್ರೆ odd integrand ಇತ್ತು, but ಇಲ್ಲಿ even integrand ಇದೆ. So whenever you have the even integrand, so this integral, so integral minus infinity to plus infinity z square e to the power minus z square by 2 dz, so it will be equal to root 2 pi. So that you need to remember. So we have 1 by root 2 pi outside, and the integration of this, it will be resulting in the value root 2 pi gets cancelled. So here this will be equal to 1. So here the variance of the Gaussian random variable, it is equal to 1. So this is the second example. And next, the expectation operator, it can be applied for the linear transformation equations also. So here we have seen the properties of the expectation operator, and we have seen that expectation operator, it can be operated as a linear operator. So what do you mean by linear operator? Suppose if you write the expectation of g1 of x, so this is some function, generally we are taking a plus g2 of x. So this can be expressed as what? Since it is a linear operator, it is independently expressed as expectation of g1 of x plus expectation of g2 of x. So this property we have seen in the previous classes, and along with that also we have seen that expectation of constant multiplied with the function, it can be expressed as c into expectation of g of x. So whatever this property we have studied, so this can be applied to some of the transformation function. So here one famous transformation function is, we can have y is equal to ax plus b. So this is considered as the linear transformation function. So here the random variable x, it can be transformed into another variable y. So here random variable x, it can be transformed, it can be converted to another random variable y, and that can be done using the equation y is equal to ax plus b. So now for such transformation function, you can apply the expectation operator, which acts as a linear operator. So now for this equation, suppose if you ask to calculate the expectation of y, so expectation of y is nothing but the mean of the random variable y. So this can be written as what? You can apply the expectation operator to all this equation. So that is expectation of ax plus b, and you can split up. So your expectation of ax plus expectation of b. So here see, a is a constant, b is also a constant. So here you can rewrite this as a into expectation of x expectation of constant is nothing but a constant itself. That also we have seen in the properties. So here we can write this equation as a expectation of x is nothing but the mean of the random variable x. So here you can replace that as mu x plus b. So here you can see that for the transformation function y is equal to ax plus b. So suppose if you calculate the mean of this transformed variable y, it will be expressed in terms of the mean of the random variable x. That is, we can write this as mu y is equal to a mu x plus b. So you need to remember this while because in the exercise problems you will come across such problems. So at that time you may need all this equation. Similarly, for the same linear transformation, you may also ask to calculate the variance. So variance of the random variable y. So that is expressed as sigma y square. This is nothing but expectation of y minus mu y whole square. Suppose if you ask to calculate this. And here you can see that we have a minus b whole square formula. So you can expand and simplify this. So here this will be resulting in y square plus mu y square minus 2y mu y. And applying the linear property, expectation of y square, you can rewrite that, or you can just a minute. So here we have the equation of, we have seen that y is given by ax plus b. You can substitute that value. So here substituting that, here we can write that as ax plus b whole square plus mu y is a mu x plus b whole square minus 2y is ax plus b mu y is a mu x plus b. You can substitute all the values of mu y as well as the transformation function of y. So y is defined by ax plus b. So if you simplify this, you can get the equation as a square expectation of x minus mu x whole square. So that is nothing but a square into expectation of x minus mu x square. That is nothing but the variance of the random variable x. That is sigma x square. So this is one format. So we can go with the alternate method also. In the alternate method, that is sigma y square, which is equal to expectation of y minus mu y whole square. So instead of expanding this, so within the bracket only you can substitute the transformation function as well as the mean of the random variable y, and then you can expand the square. So here we have y as ax plus b and mu y as a mu x plus b. Here only you can simplify this square. So here expectation, so ax plus b minus a mu x minus b whole square. So minus b plus b gets cancelled, and here we left with expectation of ax minus a mu x whole square, and in both the terms a is common. So here you can take that outside since we have a square. So I'll take a square expectation of x minus mu x whole square, and again expectation of square of the random variable x about the mean is nothing but the standard variance of the random variable x. So here you can write that as a square into sigma x square. So this is the easiest method. You can go with this. So first simplify the terms within the bracket by substituting all the equations, and you can go. And we have some more problems. We'll take one more problem and we'll wind up. So let us take the next problem. So let us consider a random variable x which is uniformly distributed between 0 and 1. So that is, we are given fx of x as 1, which is distributed between 0 to 1, and it is 0 for other values. So here in such cases, you may ask to calculate the mean about the origin, that is mu x, and the variance sigma x square. So how we are going to calculate mu x? So this is nothing but the integral. So minus infinity to plus infinity x into fx of x. So that is equal to, since we have the value only between 0 to 1, change the limit from minus infinity to plus infinity as 0 to 1, x into fx of x is 1 into dx. So that is nothing but x square by 2 with the limit 0 to 1. So that is equal to 1 by 2. And the sigma x square, similarly you can calculate this. So just rejoin the meeting in 2 minutes. I'll just wind up, rejoin the meeting, we'll continue with the problem.